The feed ethylene stream is split into two streams consisting of 83% and 17% of the original. The 83% stream is reacted with equal molar parts chlorine and fed to a plug flow reactor in which direct chlorination takes place, which attains a 95% conversion. Ethylene dichloride is the sole product of the reaction. The reaction is catalyzed with a constant amount of solid ferric chloride, which exits the reactor as part of the effluent, gets separated wholly from it in a component separator, and gets fed back to the reactor in a continuous loop. The pure product stream is fed to a distillation column, with the bottoms consisting of pure ethylene dichloride and trace amounts of chlorine and ethylene, and a distillate consisting of chlorine and ethylene and trace amounts of ethylene dichloride. The distillate will be fed to a second column which separates the ethylene and the chlorine from each other, whose subsequent pure streams are fed back to locations as seen on the screen. The remaining 17% of the ethylene feed is reacted with twice the molar amount of hydrogen chloride and half the molar amount of oxygen in an oxychlorination reaction in another plug flow reactor. Ethylene dichloride and water are produced as a result of the reaction, which proceeds to 99% conversion. Effluent is then passed through a pressure release valve, exiting at 1 atmosphere and passed straight through to the furnace. Pyrolysis, or the thermal cracking of ethylene dichloride, takes place in the furnace, producing vinyl chloride monomer and hydrogen chloride in equal molar amounts with a conversion of 55. The effluent is cooled to 80 degrees Celsius and combined with a methanol stream at the same temperature. The mixture is then cooled to 60 degrees so the methanol and ethylene dichloride can condense for reasons necessary for the following reaction, which are described in the report. The hydrogen chloride gas reacts with the sodium hydroxide solution via neutralization to produce water and sodium chloride at full conversion. The solid sodium hydroxide reacts with the ethylene dichloride in the methanol to produce vinyl chloride, water and sodium chloride at 95% conversion. Component separator to remove unreacted sodium hydroxide and the sodium chloride, i.e. the solid salts. Gas mixture is distilled, with the distillate containing all of the vinyl chloride at the desired purity, as well as small amounts of oxygen and ethylene. The bottoms contains the methanol, water and ethylene dichloride and trace amounts of ethylene. The bottoms is then fed through a column which passes methanol and ethylene dichloride out the top and water out the bottom.
When modelled through our Aspen simulation, the following values show an overview of the various energy demands throughout the process. Now, the highlighted values show the most energy demanding units in the process, as they are a magnitude of times 10 to the power 7 and are therefore considered as part of the potential energy saving strategies. The most energy consuming units are positive and the most energy generating units are negative. The following table will show the respective units and explanations for the previously highlighted energy intensive values. In order to mitigate such energy-intensive units and to reduce energy consumption as a whole across the process, potential energy-saving strategies have been created. The first strategy is to use a network of heat exchangers, inclusive of some of the most energy-intensive units in the process, to make heat transfer between specific streams more efficient. From this network of 7 heat exchangers and its associated streams, we anticipate to make energy savings of 93% and 87% for hot and cold utilities respectively. However, to maximise cost efficiency for this reduction in energy, there is a trade-off between the cost of implementing and operating the heat exchanger and its ability to efficiently transfer heat between streams. Hence, hexes 1 and 7 could be removed to still allow for a considerable reduction in energy, but to also save significantly on process equipment costs.
The prime candidates in our choice of models for our process consisted of the SR-Polar, Peng-Robinson and SRK methods, which were all chosen on the basis of their applicability to non-ideal hydrocarbon mixtures. The SR-Polar method was deemed the most suitable in comparison to the SRK and Peng-Robinson, as the latter most is idealized for non-polar molecules, whereas the SR-Polar is suitable for both non-polar and highly polar molecules. Furthermore, the SR-Polar method is more suitable and accurate at high operating conditions in comparison to the base SRK method. The limitation of using the SR-Polar revolves around the accuracy that may be lost in sections of the process whose temperatures aren't considered high. The reactors across the simulation were chosen to be the R stoichiometric reactors as opposed to the R equilibrium or Gibbs reactors, purely on the basis that each of the reactions featured in our process are non-reversible. In similar veins, the DST-WU columns were chosen at a compromise between attaining accuracy and sufficient data and working with data limitations, as a simple separator such as separator 2 doesn't provide enough due to its limited input, while RADFRAC models will require inputs which are unavailable, deeming the use of the DST-WU column with the nominated quantity of trace as an appropriate compromise between accuracy and simplification.